Good afternoon and welcome to NASA headquarters. I am NASA Public Affairs Officer Trent Parado. Today marks an important day, an important anniversary in recent NASA history, as 1 year ago the Mars Science Laboratory's Curiosity Rover landed on Mars to begin its mission of scientific exploration. It dared us all to do mighty things, and it may have even brought back the Mohawk. We have a very exciting event planned for all of you today. We will hear a little bit about the science and some of the science highlights the mission has enabled over the last year. We'll talk a little bit about the robotic follow-on missions that are planned for Mars in its footsteps. Of course, talk about new technologies and development at NASA and some of the work happening around the country and in space to enable that ultimate agency goal of a human mission to Mars in the 2030s. This will, of course, include a very special and rare opportunity to talk to Chris Cassidy and Karen Nyberg, who are currently the two U.S. crew members aboard the International Space Station for Expedition 36. So that'll be a fun opportunity. We're looking forward to it. So, if you're joining us online, you can, of course, find out more about the mission at nasa.gov/curiosity. You can ask us questions on social media. You can find us at NASA and at Mars Curiosity. And, of course, you can use the hashtag 1 year on Mars to join the conversation there. Use the hashtag Ask NASA, if you have questions for us and our speakers as we go through the event. So, we're going to start off the event by talking a bit about science. Our first speaker directs the planetary portfolio at NASA. That means every mission on or around other planets in the solar system, even the not-a-planet Pluto. We have a mission headed there. But it certainly includes the current and planned follow-on missions to Mars. Officially, he is the Planetary Division Director for the Science Mission Directorate here at NASA headquarters in Washington. Please help me welcome NASA's Jim Green. Jim?
Thank you. Thank you, Trent. Indeed, I want to welcome you on our first anniversary of Curiosity landing on Mars. And if I could have my next slide, please. There we go. And in particular, I want to talk to that new generation, the Mars generation. These are individuals that believe and will be going with us to Mars. They, of course, perhaps will think of Mars in this way, standing on the surface looking back at the Earth. So the Mars generation is here today, and our plans are indeed to put humans on Mars. Next slide, please. What I'd like to do as we go through this is really talk about some of the past missions. For us to be able to put humans on Mars, we have to take steps. And for our first rover step, here is Pathfinder. And of course, you called it Sojourner. It's our first major step to Mars, and we learned so much about how to rove on Mars and much more about the environment that existed in. And as you can see in the map, you can see where Sojourner, or Pathfinder, was located on Mars. Our next environment was indeed this one. This is the Mars Exploration Rover. You named it Curiosity. We had another one called Spirit. And these, as you can see in the particular graphic, show us where Spirit and Opportunity landed. Of course, Spirit, unfortunately, is no longer operating, but Opportunity is doing well. It's wintering over right now as we move from summer into the winter season, and it's doing a great job living 10 years in a time when we only thought it might live 3 or 4 months. Our latest rover, of course, is Curiosity. Now, this is a nice little mock-up of Curiosity. It's huge. It's about the size of your SUV, and even this doesn't do it justice. The top of Curiosity is actually here, and as a 6-foot individual, I have to look up to Curiosity. Here's one of the wheels. This is a wheel that we used for testing, and as you can see, it's gone through the batter test. But that was, of course, necessary for us to test all elements of that 7 minutes of terror and actually making that landing, going from 13,000 miles per hour when it hit the top of the atmosphere to only inches per second when it actually landed. And, of course, it landed safely, this time 1 year ago. And not only, as we're going to find out, is it discovering the past of Mars, it's actually making major discoveries about what Mars is like today. That's important because our future is really in our hands. Our destiny is to leave low Earth orbit, trek out into the solar system. The solar system is ours. Let's take it. And we believe humans can actually land on Mars as that ultimate destination for humans within 20, perhaps 30 years from now. So let me now talk more about the science. Next slide, please. Here's where we chose for Curiosity to land. It's called Gale Crater. And as you can see in this color rendition of height, the lowlands are blue, the highlands are on the order of green and also red. And it's at that boundary between lowlands and highlands. We picked that particular area because we wanted to go for understanding if Mars had a very wet history in its past. We see a lot of indications that Mars has had water on its surface, but we really wanted to see if water could have existed for long periods of time. This seemed to be the perfect place. It's a lowland area, and that, of course, is where water would exist. Next slide, please. Here's where we landed. Right smack dab in our bullseye called Gale Crater. You can see where Curiosity is, as pointed here. You can see where the jets from the sky crane blew away the topsoil. You can see that the sky crane actually detached and crashed much further away. But you also see areas like this fractured unit and this cratered unit and this hummocky unit. Mars was, in this location, was just a fabulous opportunity for us to take a really good look at what's around us. Next slide, please. And of course, we took our own beauty picture. This is 54 frames from our ARM camera, and someone in the community on the internet did this. Next slide, please. Put the picture together and gave us a great look of Curiosity on its surface. Next slide, please. All Curiosity had to do now was to look around, wake up, get its instruments up and running. It looked north towards that crater rim. And of course, on the other side of the crater rim is that very low-lying area. In fact, we see from orbit major scours that exist in that crater rim where water perhaps poured over and into the crater itself. Next slide, please. It also looked towards Mount Sharp. Here is its ultimate destination. Next slide, please. What's really fabulous about Mount Sharp are these structures, these linear structures that run across. These are layered sediments. Geologists call this stratigraphy. This is literally the pages of the history book on Mars. By going to Mount Sharp, we're going to be able to unravel that history and look at what happened over time and why Mars's climate is so different than what we believe it existed 4 billion years ago. Next slide, please. This little boulder that we point out, this little tiny boulder that's sitting in front of us is actually the size of Curiosity, our 1-ton SUV-sized vehicle. Next slide, please. Curiosity began immediately to look around and begin its science phase. And here's what it found. On the right, we see similar structures on Earth. These are conglomerates of rounded pebbles. These are found in dried up river beds. On the right, we see exactly the same thing where Curiosity is sitting. And in fact, we now believe that Curiosity landed in an ancient riverbed. Water that flowed in this area billions of years ago, maybe for tens of thousands and millions of years, flowed in this particular region. Next slide, please. Well, this was exciting discoveries, and now we turned our attention to the next set of experiments. And that's where the arm could sit down on a particular location, on a rock, and drill. Next slide, please. And so here's the rock that we chose. This is a sedimentary rock. This is material that's been laid over time at the bottom of what we believe is this ancient riverbed. Next slide. It drilled this hole, and as we get closer to it, next slide, we see quite clearly that Mars is a different color underneath its red surface. This is gray Mars. This is Mars of the past. When we began to analyze this data, next slide please, Putting it in our scoop and putting it in our sophisticated science instruments, we found carbon, we found nitrogen, we found oxygen, we found phosphorus, we found sulfur. We found all the ingredients of life is measured in this material that's deposited in this ancient riverbed. Mars was habitable in its past. Mars was a blue planet. This has really been a major step forward in understanding that Mars was much more like Earth many billions of years ago. And of course, now we want to understand what happened to it. How did it change from the environment that was much more Earth-like to what it is today? Very dry. And in fact, the atmosphere is only 1% of what ours is in terms of its pressure. And it has quite a bit of difference in composition. Next slide, please. Here's our destination. It's called Mount Sharp, as seen from our Mars Reconnaissance Orbiter. We're looking down now in the bottom of Gale Crater, near the landing site. You can see where we went to Glen Elg. That's where we found the conglomerates and did the analysis I just referred to. We're heading towards the base of Mount Sharp right now. We're moving anywhere from 40 meters to 100 meters per day. Now, this is about a journey of 8 or so kilometers, so it's going to be several months. And along the way, we'll find some fascinating things, I know. Once we get to the bottom of Mount Sharp, we're going to have to avoid this black area that you see. This actually is our sand dunes. From orbit, we see these sand dunes shift around. And of course, as every good golfer knows, we want to stay away from those, maneuver through those, and begin to crawl up Mount Sharp and begin to analyze these layers of history, this stratigraphy, the laying down of sediments that have occurred over billions of years. And putting all that together will enable us to understand what happened to Mars, going from a habitable environment, as we now believe it was in its past, to what it is like today. And of course, today, that is important data for us to be able to understand, next slide please, what our future might look like. Now this actually I pulled off the internet only days after this particular picture was taken. Someone from the Mars generation made this beautiful image. Of course, it is overlaid with the shadow of Curiosity late in the day as the sun went down, taking their transformer and a shadow of that, photoshopped this in. But in reality, this is what humans are going to look like in 30 years on Mars. They're going to have communication with their orbiters. They're going to be having a set of tools. They're going to be working on Mars. They're going to be living on Mars. And of course, they're going to have their pet dog rover right there in hand, helping them along the way. The next major mission that we're thinking of along this path is a rover much like Curiosity in terms of its volume, its size, and its mass. However, it will have a completely different set of instruments. We're planning to launch that in 2020. We're planning to take that next step, knowing that Mars was an environment that was habitable in its past. We're going to start seeking the signs of potential life that could have existed on Mars. And that, if we can answer that question, will change everything. It will tell us that life not only may exist in our solar system, but throughout our universe. So these are huge steps, and we're making great progress. And so for all of you, we want to take you along in the journey. So with that, maybe I can take some questions in the time I have remaining.
Thanks very much. We have a couple of roving mics, and I think we have, let's see, do we have our first question down here in the front?
Hi, Jeff Wall. Jeff Wallace, and 528 on Twitter. So, what would be your top three biggest challenges and things that you're now happy about?
Okay, the top three challenges are indeed making sure that all the systems are put together in much the same way that we have with Curiosity to be able to get that next rover down. Also be able to get the right set of experiments together that do that major step in seeking signs of life. That would be the next major one. And then, of course, we have to find the location that we want to go to. Like real estate, it's location, location, location. You know, the Vikings in the 80s, when they sat down on Mars, and they were a life experiment, and they scooped and made measurements of that, that was pretty inconclusive. In fact, most scientists believe that Viking results didn't indicate that there was life on the surface. But Viking landed in modern Mars, bathed in ultraviolet radiation and cosmic rays. Curiosity has gone to a place that's been unmodified in 3.5 or so billion years. It literally went to the right place back in time. And that enabled us to really see what Mars's past was like. And that's what we want to do next. Find that next fabulous location, undisturbed, in its past, where life could have existed.
Let's take a quick question from social media, if we could.
Sure, we have a question here from Twitter user Sheldon C. Has anything you found on Mars in the past year triggered plans for additional questions, research, and exploration?
Yes, indeed. Just about everything that we find out, we want to know more about. For instance, not to get too technical, but we looked at, from the atmospheric instrument, ratios of argon. There's different types of argon, one argon heavier than the other. Argon doesn't react with anything, but it has a natural amount of each of those elements throughout the solar system. And when we were at Mars and we made those measurements of argon, we found the lighter argon had left. Mostly the heavy argon was there. The only way that could have happened is that Mars's atmosphere was stripped away. It changed. Where did it go? How did that happen? So our next big mission, MAVEN, which will be launched in November, is designed to go to Mars, be able to orbit and look at how the solar wind interacts with a planet that no longer has a magnetic field. You know, Mars lost its field billions of years ago. And we want to know why that happened. But we want to see that process and whether the solar wind actually did the stripping or something else happened to its atmosphere. So just each and every one of those discoveries builds on the next set of questions we want to answer.
Show of hands for questions we haven't gotten to yet. Okay, here in the middle.
There's an MRO image a while back that showed what seemed to be liquid water flowing seasonally on Mars. Is there any plans to get closer to things like that?
Yes, the beautiful images that you were referring to, we actually see fairly often now because we know where to look. They occur during the summer when crater walls are such that they get the maximum sunlight. Now, what must be happening is that sunlight is sublimating, in other words, going through that process of solid to vapor, the aquifers that are plugged up. That releases what's inside these aquifers, which we believe are briny water, which flows down the crater walls. You can't go anywhere on this planet and grab a thimbleful of water without finding life. All right? So the fact that Mars has trapped water inside it still bodes well for potentially finding life, even perhaps today. Well, the aquifers are pretty deep. We still have a lot to learn before we know where to go. We need to understand how close they are to the surface and where we might be able to investigate those in the future. In the meantime, as I mentioned, after MAVEN will come our Mars rover in 2020, and that one is going to bore holes into rocks and look back in the past. And it's really the past that we have the greatest chance to find out if Mars was ever inhabited. That should leave remnant material, organic carbon, all the right stuff. And that's what we want to look at next. That will be our next step. But the briny water is really intriguing, and we do want to follow up on that someday.
Hey, Jim, before we lose you, what are the follow-on missions that we should be looking for here?
Well, the one we're launching in November is MAVEN. It is an orbiter, and it's designed to be able to look at how the ionosphere and atmosphere of Mars interacts with that outgassing from the sun called the solar wind. And we know that solar wind may be stripping atmosphere away, and we want to see that process, and we want to see what it's losing. And that will tell us a lot about what's happened to Mars with respect to those processes over millions and millions of years. Our next NASA-led mission is indeed the 2020 rover. We'll launch it in 2020. It will land about 9 months later. We will use the scary sky crane, as everyone has called it in the past. We'll relive that 7 minutes of terror, I'm sure. But what we put down on the surface will be a completely different set of experiments, and we'll be taking that next step along the way that allows humans to go to Mars in the future.
Let's give a big round of applause for Jim Green. Thank you for joining us.
Thank you very much.
Okay. So now we're going to talk about one of my favorite subjects, I'm sure many of yours as well, which is technology. Research into space, and the things that NASA accomplishes inevitably improves lives on Earth as well, through the invention and innovation of new technologies. The journey to Mars, to an asteroid in Mars, for NASA is not going to be any different. Our next speaker directs cross-cutting technology innovation and development for the agency. He is the acting director of the Strategic Integration and Analysis Office within the Space Technology Mission Directorate here at NASA. Please help me welcome Prasan Desai.
Thank you. Good afternoon, and I'm very happy to be here. What I'm going to talk about, next slide, please. Jim Green just laid out a nice overview of the Mars program from recent history and what we're planning to do over the next 10 years, say, to do robotic explorations. But what I'm here going to talk about is how do we actually put boots on Mars? One of the things that we as a country want to do is explore deeper into the space beyond low Earth orbit for humans. And there are a lot of challenges for that to occur. We've done a very good job of getting astronauts into low Earth orbit in the vicinity of the Earth-Moon system over the years. But to get further out into deep space, there are a number of areas of technology we need to invest in. We've made a number of these investments, and I'm going to talk about what we're doing now, but we need to make some sustained investments for a decade or more before we can get the reliability and some of the capabilities we need to send astronauts to the surface of Mars or deeper into the solar system. And what this chart kind of shows here are a number of the areas that we need to make some investments in to really improve the capabilities. And they span many different areas for sending spacecraft and humans into deeper space. And one is better communications. Right now we use radio frequency communications that when we send robotic spacecraft and even astronauts into low Earth orbit. But we want high band communications. When we send humans, we're going to be getting a lot more data. If we want really video, those types of things, we want a high-speed internet, basically, to be able to bring those data back to here. And so some of the investments we're making on is improving the communications capability. Life support, obviously. To send humans outside the Earth, we require a life support system for them. We have a lot of experiments going on at the space station to improve the reliability of an environmental system for long duration operation. We need to test those out, make them much more higher reliability, so when we send astronauts to deeper space or to Mars on a mission, we would have systems that would provide everything they need for daily living, from breathing to food, recycling, waste, so on and so forth. Because a mission to Mars for humans is going to take anywhere between 2 to 3 years. And so it's a long way to go and a long time to come back. And we can't just go there and fix things, okay? So we have to have systems that will be highly reliable to be able to take care of the astronauts to not only live, but the reason they're going there for is to do this scientific investigations that Jim talked about that we do robotic systems with, but all the other things that humans will bring into that aspect to be able to figure out what's near what's within our solar system and near to our planet. And Mars is really the next big hurdle for sending humans deeper into space. Power generation storage, they're going to need power to operate not only what they need, the astronauts, but all the equipment to do the analysis or roving on Mars and so on and so forth. So we have to find ways of generating power and storing it so they can utilize it for the extended period of times that we will be doing that. You see, Spirit and Opportunity, Curiosity rovers there, solar power, and Curiosity used a radioisotope generator to produce the power. We're going to need a lot more power for when humans are on the surface with a lot larger vehicles to be able to operate those types of systems. Logistics, how do we pre-position large things on the surface of Mars? Curiosity allowed us to land 1 metric ton on the surface of Mars. To you, that may sound like very big, right? It is. Trust me, because I spent my previous life here at NASA at one of the space centers in Hampton, Virginia, NASA Langley, as an entry, descent, and landing engineer. I helped land actually Spirit and Opportunity as well as Phoenix. So I know the challenge of landing something. We barely are able to do a metric ton now. When we send humans, we're trying to land 40 metric tons. So we landed a car. What we need to do is a 2-story house when we send humans to Mars. How do we do that? We don't have a good method of doing that right now. And so some of the investments we're doing is based on trying to do those types of things, and I'll walk you through a few of those. Navigation, figuring out how precisely we can get there. Manufacturing in space and for space, we would like to create what we need when we get there. So if we take what you've heard of, 3D printers, we can manufacture tools if we need to right on the spot. If we don't have something, of course, if we didn't bring something and we need something like that to repair something, or we find something on the surface of Mars that, hey, we really would like a tool like this. If we didn't bring it, we wouldn't be able to do it. So a lot of investments in 3D printing, we're trying to take it to the next level where we can actually manufacture the material we need. And then once we're done with it, recycle it so that that material can be used to create other things. We're also doing food creation with 3D printers to see if we can develop food that way for the astronauts to eat, as opposed to getting some stuff that's freeze-dried for years upon prior to them departing. So we're making investments in trying to figuring out how to do those things real time. Propulsion is a big aspect of how do we go deeper into space more efficiently so we can take much more infrastructure where we need to. To this point, we've only done one-way missions to Mars. When we send humans there, obviously we want to bring them back. So that would be a round-trip mission. There's no gas stations on the way, okay? And so, or convenience stores, for example, for food either. So we have to take all that with us. And so we need a propulsion system that will be very efficient to minimize all what we need to take, in particular the fuel, to be able to get to Mars, do what we need to do there, and come all the way back. Entry, descent, and landing, as I mentioned, we have to land something about the size of a house, a 2-story house on the surface of Mars, and I'll talk about some of those investments. We talked about the 7 minutes of terror. The reason why it's 7 minutes is you fall very quickly. We have to land something very large in the same amount of time, and how can we land something that big? And then radiation protection. Obviously, when we go into deeper space, we want to make sure that the astronauts are well taken care of, and so we're making investments in those areas as well. Next chart. So I talked about in-space propulsion. That is a large, tall tempo that we need to get over. And one of the areas we're investing in right now is solar electric propulsion, because it is a very fuel-efficient way of sending things into deeper space, or even around low Earth orbit for that matter, and I'll talk about that in the next chart. So we are investing in propulsion systems that we can use new methodologies to be able to send large equipment at a very efficient, low fuel usage. We're making investments in the solar array technology, how we can use the sun's energy to produce the power that we need to expel a propellant like argon or xenon, some other type of thing, through an engine, and what you see in there is thruster development, as well as a high power processing unit, where when you have something very high power that you're generating with those solar arrays, you need to condition it so that you can utilize it for the various systems, be it for propulsion like an engine or the onboard computers and everything else. We're making investments in that. And then obviously the structure of where we put the fuel in, the structure of the spacecraft, of finding lightweight, strong materials that allow us to be able to put a spacecraft together that's very lightweight and use that savings to put into the useful aspects that the astronauts need and the equipment we would need to go to deeper space. So we're making huge investments in solar propulsion right now. That will go towards testing out in the asteroid return mission that many of you heard about. As Jim mentioned, we did steps from a small rover to kind of get our feet wet, figuring out how to do that on Mars, to larger ones, and then Mongo ones like you see here with Curiosity. We're going to take the same approach with many of these systems, is test them out with, for example, this asteroid retrieval mission of the propulsion system, how can we do autonomously all these aspects of operating in space when at distances when humans aren't nearby. And then also when we bring this asteroid closer to us, about how astronauts will live and work in space going and looking at this asteroid. So those types of investments is what will allow us to do by working on this asteroid retrieval mission, and propulsion system here would be one of the major elements of that. Next slide. One of the aspects of solar electric propulsion, which is SEP, is you can do so many different things with it. And here's just a list of a few of them, where in low Earth orbit you can do satellite servicing, where if you want to refuel a satellite or repair a satellite, you can use this very efficient way of getting to it, repairing it, moving on. Delivering payload to higher orbits, we use a traditional rocket to get into a lower orbit and use this solar electric propulsion to boost it the rest of the way. It's much more cost effective and fuel efficient than systems we have now. Orbital debris removal and moving so that we can get things out of the way, that the space junk, it will make those types of activities much more cost effective, as well as other missions we want to do in the solar system where it can send things out further in a much more cost effective manner than traditional rockets that we have today. So it allows us to do a cross-cutting type of capability with this type of investment. Next slide. So here, it's talked about the Mars, the challenges of deep space, but here specifically going on Mars challenges. I'm not sure if you can read all the wording on there, so I'll walk you through a few of them, and the charts will be available for you guys to look on the website. But surface power, I talked about that. Once you get to Mars, what are you going to do in terms of power that the astronauts will need and the equipment to be able to do everything we need. Life support, we're making investments, and I'll talk about a few of these on the next chart when we get there. Operating on the surface operations, how do you go about doing that with robots and things to help the astronauts multitask in many ways to be able to do that. Mars resource utilization and ascent from surface. As I mentioned, we've only done one-way missions to this point. So if we send humans to the surface of Mars, we want to launch them back up and be able to come back, and we want to, in essence, live off the land to be able to do that. Entry, descent, landing, I talked about communications and getting to Mars in terms of in-space propulsion are many of the same challenges about going deep space as going to Mars as well. Next slide. This chart basically just takes some of the solutions that we have into those 8 elements that I just talked about. I will focus more on the next slide, but it just gives you a few of the areas. So we're talking about a surface power of fuel cells and batteries, as well as in life support, a closed-loop life support system, so we can recycle all the material that's going on for the astronauts. And so the amount of water we need to bring, the oxygen we need to bring, would be minimized to be able to reuse those. So just a couple of those elements, that solutions that we're talking about. Next slide. So let me talk about a few of the elements that in our STMD, Space Technology Mission Director, which stands for the advancements we are making. You can see on the right-hand side there, my right, entry, descent, and landing, there's a lot of activities going on. The reason being is we don't know how to land 40 metric tons. And we're trying to figure out systems to be able to do that. And we're trying to do many different types because we're not going to know which one is going to win out in terms of the best capability. But also, when you land something going 13,000 miles per hour when you get to Mars, you have to go through every flight regime to get to the ground. While if you're in an airplane, you go all subsonic. So you only remain in one flight regime. You have to have different systems in all these different flight regimes to be able to land these types of things. And so you need systems in all those different areas. And so we need to make investments to figure out how best to slow down in those different speed regimes to be able to do that. We're making investments in life support for closed-loop systems. We're testing those out on the ground right now, and we will test them on the space station so that we can demonstrate them, that they are working properly like we need to get the high reliability to be able to send humans deeper into Mars. Go on to the next slide. Here's a few more investments in terms of Mars resource utilization. Let me kind of leave you with this thought-wise. I spent most of my career at NASA Langley in Hampton, Virginia, just south part of Virginia. Jamestown settlement is just a handful of miles up the coast. When the settlers came here, maybe settlers weren't the right word, but the explorers came here long ago, they brought what they needed to come to the new land, just for the transit. and then they lived off the land once they got here. This is what we're trying to do with human missions to Mars. Because if those ships had to bring everything there with them to live in the Jamestown area, that endeavor would have been so expensive and so large that would have made it very prohibitive for anyone to authorize to go. And when we go to Mars, we have to bring the air with us too, not just the water to drink or something like that. And so we want to do something similar when we go with humans to Mars, where we utilize the atmosphere there on Mars to be able to extract the oxygen from, so that we don't have to bring all that oxygen with us, so that we can use that to breathe for the astronauts. We can make rocket fuel out of it, freeze it, so that it's liquid oxygen that we can use for propellant, so that we can launch off the surface. So we want to move and explore in a very similar manner that we've done in the past, so that we can live off the land to make all these missions very cost-effective and more efficient, to be able to conduct what we're trying to do, which is explore Mars in a much more aggressive manner, so that we can actually really get a sense of, are we alone in the universe? We're making many other investments, and those are just a few that I wanted to talk about right now, and I'll be happy to take some questions.
Yeah, let's take some questions on technology. Here in the front, Lauren. Oh, I'm sorry. Go ahead.
Hey, so you were talking about using entry, descent, and landing for human exploration. Is there a physical limitation to the amount of mass you can bring to another planet with that?
So the only physical limitation is what our systems would be capable of either launching off the surface, or once we get there, being able to slow down. And so it really comes down to what kind of system do you design. And right now, we're limited to about 1 metric ton because of the type of technology we have to be able to land it. And so if we improve that technology, we'll be able to increase that payload to be able to get to the surface. But there is no physics reason why we can't land more payload.
Can we go here to the front?
What's the status of the laser communication technology that they're trying to use from the space station? Is it on track? Or?
Okay, so we have a investment right now in our laser communication to relay demonstration, where in a few years we're going to demonstrate optical communications from orbit down to the ground to be able to get much higher speeds of bandwidth there. It is progressing very well. We hope to, by 2017, launch it and be able to do that demonstration. We also are looking at deeper space communications with that. That's a low Earth orbit communication. No, I shouldn't say low Earth, from geosynchronous orbit down to the ground, so we'll be able to do entire vicinity of the Earth. We are trying to extend that to even further deep space activity, and so we have early investments in what it would take to extend that capability even further out in terms of into the solar system, and we're making those investments now as well. And so hopefully in a few years, we would be able to get an optical system for communications for not only NASA's use, but for commercial use, where all those communication satellites in geostationary orbit would be able to provide that as a service to everyone on the ground for much more bandwidth capability than we have now.
Let's go to social media for a question.
Sure. So Google Plus user Josh asks, based on what you have learned from Curiosity in the last year, are there hardware changes that you wish it possessed? If you had to rebuild Curiosity from scratch, what would you do differently?
How many hours does he have to talk about? No, entry, descent, and landing is a very difficult endeavor just in aspect. One of the things that we call Mars the Goldilocks planet. The reason being there's not enough atmosphere to really help you slow down what you need like you do at Earth. When you come down, it slows us down so much that it makes it much easier to land heavier things on Earth than Mars. But there's just enough atmosphere that you have to worry about all these other things. If you land on the moon, you don't have to worry about thermal protection systems because there's no atmosphere. You just propulsively come down slow and land things. And so for Curiosity, we're not going to make any changes for the next landing that the previous speaker talked about for landing in 2020. The system worked great. We always have data that we get back from there, and we in fact had our heat shield on Curiosity instrumented with sensors that we are downloading the data and analyzing it right now on how everything went. And based on that, we would make what we think are best adjustments to that before we do go on to the next landing. But everything we saw worked very well. I think we in one thing is we didn't use as much fuel that we had put on the system, and so we can look at trades of, hey, since it went so well, we can minimize the fuel we put on there and add more payload capability to put more instruments to figure out what on Mars. So we would talk about those types of changes, but the system worked so well that I don't believe we were going to do any wholesale changes except some tweaks here and there to just improve the performance from where it was.
Okay, please help me thank Prasen Desai, everyone. Thank you. Thank you very much for your time, sir. All right. We are closing in on our conversation with the International Space Station about 20 minutes from now, which means, I don't know, it'll travel a quarter of the Earth in orbit between now and then. Here to help us understand a little bit more about some of the research and technology that's taking place above our heads, some 220 miles, moving 17,500 miles an hour and orbiting the Earth every 90 minutes in a national laboratory that's helping solve some of these challenges that you just heard. Our next speaker actually directs the International Space Station program here at NASA headquarters in Washington. Please help me welcome Sam Shamimi. Sam?
Thank you, Trent. Next slide, please. While one part of NASA has been launching robots to Mars and exploring the surface, another part has been launching people into space to the International Space Station. We are today, and for several years now and many years in the future, are working to send, to do the research and technology demonstrations on board Space Station to get humans to Mars. Next slide, please. Well, you might ask where we are today as far as getting people out into space. Well, today, the space station is about 400 kilometers away from Earth. It only takes about 6 hours to 2 days transit time to go back and forth. And the communications is near real time. And we have crew exchanges that go back and forth every 6 months for the station. And we have atmospheric samples and crew samples that come back to Earth that can be analyzed to check if the crew's healthy, if the atmosphere is healthy, research samples and the things of that nature. And we have supplies and logistics that get launched to space station that way we can repair things and get extra supplies up. We also have things as mundane as removing trash from the space station that burns up into the atmosphere. And most importantly is that we can return the crew at practically any time to come back in case of a on-orbit anomaly or a crew emergency. So what you're looking at today, what we have in space, our technology and our knowledge, we're basically just car camping in space. If you've ever been car camping before, you take your car, you load everything up that you need, and you go to a campsite. If you get something, you go to Walmart. If you fall down and hurt yourself, you go to the hospital. It's all very convenient. Next slide, please. However, Mars isn't anything like that. It is completely different. To go to Mars, we have to build a capability and knowledge to essentially live on another Earth, to recreate a capability, what we just heard about before in technology and the like, to provide our own atmospheres, to remove our trash, to be able to keep the crew healthy. All those things has never been done before. Neither here on Earth has never been recreated in an environment for such a long period. As mentioned before, the transit time to going to Mars is 1 to 3 years to go back and forth. And our communication, when we get to Mars, is up to 42 minutes round trip. There is no link between Earth and Mars other than the communications. So on Space Station today, we are learning how to break all those links. Not only just how to keep the crew alive and healthy and productive, but to break all the logistics chain, break all the logistics chains, the capability to return the crew safely. When we're going on to Mars, and once you pass a certain point, you can't get back to Earth easily. You have to actually go all the way there and then come back. And then you've got orbital dynamics to consider. You can't come back just at any time, only predetermined times. So what are we doing on Space Station today? Next slide. Well, we're doing a whole lot of things, and I'm just going to only highlight a few of them here. First is the duration. Today, our crews are rotated every 6 months on Space Station, and we have, and our research and our crew health is all based on 6 months time frame. But to send people to Mars, it's going to take at least a year to get there and back. So we need to be able to understand the effects of weightlessness and radiation on the human body. So starting in 2015, we'll start our first one-year crew increment to understand the effects of bone loss and muscle loss on longer periods. Also on ocular vision, we've had some issues with ocular vision on the astronauts that have been aboard space station for 6 months. So learning how to do that to keep the crew healthy and to keep them psychologically healthy and things of that nature, we're going to try that for the first time in 2015 for a one-year crew increment. Starting on the right side is the second most important thing is environmental control and monitoring system. Today, it takes a lot of maintenance and a lot of crew time and ground time to keep the environmental control and life support system functioning properly. We are making modifications to the system today to increase its reliability and performance. And in the next few years, we hope to have the Mars system for the environmental control system on station operating. And it'll be that system that we fly on the ISS that we take to Mars. Down from there is the crew health and monitoring equipment. And a couple slides back, you saw that we have all the crew samples and air samples that come back as far as blood and urine and water and the like to see if the crew's healthy, if the systems are performing correctly. When we go to Mars, we can't do that. All that has to be characterized on orbit with the crew assistance in determining is all the performance parameters in its normal ranges. Going on to the top left on your side is the exercise equipment. Today our exercise equipment is large, it has lots of moving parts, they're complex, and they take up a lot of mass and space. Going to Mars, all this will have to be a lot smaller than it is today. So we're making improvements and flying additional equipment on board the station to ensure that the crew has functioning equipment to go to Mars with. We also have onboard water analyzers, again, to break the chain of bringing samples back to Earth. And one of the other things, not the last one, but one that we're working on right now is the new exploration suit demonstration. Today our suits we have today on space station are 1980s vintage technology, so we're working across NASA to build a new suit and demonstrate it on space station. So these are just some of the things we're doing on space station today to get us to Mars. And with that, I'd open up to questions.
Thanks. I just wanted to remind the audience that's joining us online that you can ask questions of our speakers and pretty soon hear the crew using the hashtag AskNASA on Twitter and Google+. I actually want to take podium privilege real quick, Sam, and just ask a question. It's because Jim showed this really incredible picture, that fan-made image of someone in a spacesuit. Or at least a giant robot standing next to Curiosity. I know there's some robotics happening on station too, and we sometimes talk about how humans and robots will be working together to accomplish these things. Can you tell us some of the robotic experiments that are happening on the station right now, and who the robots are that are up there?
Well, let's see. How many robots do we have? So I'm familiar with at least three of the robots that are on station, and one that's on its way. First two that have been there a long time is the Canadian arm and the Canadian Dexter manipulator system. These two large robots are basically industrial robots. And we've learned a lot about assembling pieces in space, how to do ground control, how to do maintenance and things of that nature. We also have a third robot inside. It's actually half of a robot called Robonaut. It doesn't have legs yet. And we're learning how on board space station to integrate robot activities together in close proximity to human activities. So that's very important to us as well. And I think the fourth one that just was launched on HTV from Japan is, I think the Japanese are characterizing it as a astronaut friend robot. It's a smaller robot that interacts verbally with the crew member.
And if I'm not mistaken, didn't we recently have some crew members actually drive something not too dissimilar
and
from
we also
that from station?
remote controlled a robot at the Ames Research Center from the crew on board the space station to simulate actually driving robots from an orbiting spacecraft around the moon or actually Mars as well.
I geeked out about that, quite honestly. Just growing up with remote control cars, seeing an astronaut drive something on Earth was pretty mind-blowing. Do we have any questions in the audience? Right here.
Yes, these robots and robotics, they're so capable. And what is the real advantage of having a person on these foreign terrestrial places rather than just sending so many leaner, easier to get to, more efficient robotics to the Mars and beyond?
If you compare what it takes to plan and operate a robot long distances like from Earth to Mars and what a human can do, it takes a year or more for what a robot can do that a person can do in a matter of days. So one is efficiency, is that the crew member can do things a lot quicker than a robot can because it all has to be pre-planned, and with the communications lag between us and Mars, that's a real handicap. The second biggest thing, and I think more important, is you have an intelligent being interpreting its environment. A crew can immediately pick up, is this important? That's not important. And if they're trained as a geologist, they can pick up the right rock or not the right rock. So that's another advantage of having the crew members. And I think thirdly, there's a societal benefit as well to having people involved in exploration. I don't know any kids that want to grow up to be a robot or to be a rocket. They all want to grow up to be an astronaut or be a scientist or an engineer. No one's actually advocating for people to be robots, so I'd leave it at that.
So let's take a question from social media.
Sure. We have a question here from Twitter user Lucy Whitehead. There are plans to put people on Mars, but is there the possibility of people living on Mars?
Yes, I think at some point in time, once we've learned to travel there and come back and to be able to use the resources on the Martian surface, I think it one day will be possible.
Great. More questions in the audience? In the back.
So, if I'm not mistaken, this is just as a backstory, the FAA has ramped up pilot requirements to do more manual flying because there's been a lot of concern about over-automation, too much reliance on systems like that. Is there any concern about that with NASA, that we would ever get too reliant on these automated systems like the unmanned flights that are headed to the space station now?
Well, there's just some different aspects of, if you will, crew control of spaceflight. On the way up from the ground and while riding on the rocket, there's not a lot the crew can actually do other than get off the rocket if something goes wrong. However, in space, there's always the capability for the crew member to override any automated system, and the way we've designed systems in the past and the way we're designing them in the future. There are some tasks that are better left as the first level of control as automation, like automated rendezvous and docking. It's a lot more efficient that way, but the crew is always monitoring and able to back out of the system in case something's wrong. So I don't think it's an either or. It just comes down to what is more efficient and more repeatable and reliable, but always having the crew ability to back out of it in case the automated system does not perform as expected.
You know, Sam, one of the things our TV crew has is a really nice image of the International Space Station, and I think some people sort of forget. You know, we don't see it all that often. In fact, this almost looks like a live view. The sheer size and scope of what this laboratory is. Maybe you can. It's a live picture. I'm being told. Can you tell us what we're looking at here as we get ready to?
Well,
talk
what we're
through?
looking at, the appendage that you're seeing there sticking up is the Canadian arm. And you're seeing in the forefront the Columbus module with its exposed facilities. You also see the golden solar arrays sticking through at the bottom, the U.S. lab in the midsection there, and of course the Earth above. The space station itself is as large as a football field, and about 1 million pounds. It's unfortunate that the space station never comes back. People don't actually get a chance to see it. Like the shuttle comes back, when we fly the Soyuz or the Dragon vehicle, it all comes back so you can actually see it and hear it, feel it, touch it. Space station, you just can't. You can see it when it passes over. And do a little plug for Spot the Station app to find space station wherever you're located. But it's an amazing facility. It took many years and many flights to get it assembled, and that's it.
No, that's a good point. Spotthestation.nasa.gov is where you can go to find out where the International Space Station passes. I think it's pretty much the brightest image, or brightest point of light in the sky when you see it.
Except for the sun and the moon.
Yeah, and it moves quick, but when you can catch it, it's very, very cool to see. Let's go back to social media for a question, then I'll check in the audience.
Sure, we've got a question here from Twitter user GeneJM29. Since current EVA suits are 80s vintage, what is in development now, and how long will it be before those suits become available?
Well, right now we have technology development activities going on today between the Human Exploration and Operations Mission Directorate and the Space Technology Mission Directorate to develop the newer generations of scrubbers, of the life support system, new materials for the suit. Today, our suit is a multi-part suit, I would say, and our next generation suit will be more like the Russian Orlan suit, where it's more or less one piece and the crew steps in from the back. There's a picture of it right now. The suit will look similar, just for the casual observer, but the internal functions will be completely updated with newer technology, and it'll be a more compact suit as well.
Great. Questions in the audience? International Space Station. In the front.
Does NASA have a view on private initiatives like the Mars One initiative?
NASA is supportive of the private initiatives. The Inspiration Mars, I think that's the recent one that was announced. We're working with them to understand what their mission is and what help they might need from NASA. So we're very supportive of such missions. I don't know if we're actively promoting one-way missions to Mars, as NASA's is in the two-way business. But we are very supportive of private initiatives.
We like our astronauts to come home. And in the last couple of minutes that we have with you, Sam, could you explain on that note, on commercial space, kind of where we are in development of the new spacecraft to take U.S. astronauts, once again from U.S. soil? I think and people may be familiar with a couple of the cargo craft that came. If you can talk a little bit about how the space station is working on the commercial side in American development.
Well, there's two aspects to the commercial involvement in space. On space station, and also I'd like to say just more in private initiative in general. As many of you may know, we have a commercial cargo providers, SpaceX and Orbital, to provide cargo to the space station. But we're also in development with other industry partners to develop the commercial crew capability to space station with SpaceX, Boeing, and Sierra Nevada. But also, that's only part of the commercial initiative on board station. We have a partnership with CASIS, which is the national lab developer for NASA on board the space station. CASIS is working with private industry to utilize space station for things like pharmaceutical research or materials research like colloids, new medical devices, and the like. So our commercial involvement is quite broad on space station.
Is there, and real fast, is there anything that we just recently sent up to the crew that you thought was particularly cool? Any home packages or care packages or anything like that?
Well, fresh food and ice cream is always good stuff.
We'll see if we can get a question or two about that. Help me, everyone, please thank Sam Shamimi for his time. Very good. And we are now looking at a picture of Mission Control in Houston, which helps manage the International Space Station program. I understand, we just pause for a second, that we are very close to being able to talk to Chris Cassidy and Karen Nyberg, who are the 2 American crew members aboard the International Space Station of the Expedition 36 crew. So let me start by asking the station, say, station, this is NASA headquarters. How do you hear me?
Houston, this is Station. We are ready for the event.
Thank you so much for joining us, Chris and Karen. It's wonderful to see you. All right. So we're here in Washington in the NASA headquarters auditorium. We've heard a lot about Curiosity's first year on Mars. We've talked a lot about new technologies and some of the research and technology you're doing on orbit that will help enable the path for humans to Mars here soon. I want to jump into questions here. I know there will be many for you. So if you'd stand by for the first, and we will get started. Questions for the crew? Okay.
So, how are things going up there? You know, we
Very
take
well, thank you. Thanks for asking.
So I think part of the question is how is your sort of daily tasks? How are things going there day to day for you right now?
Okay, sorry about that. I think I stepped on the first part of the question. The day-to-day life is really, you know, it's a nice pace. It's a busy day. We wake up around 6, have a conference with the ground at 7:30, and then work right straight through until another conference at 7:30 at night. But in that time is a break for lunch and exercise, which is critically important for us for many reasons. But it's a nice steady pace of the day, and at the end of the day, it's really fun to eat and join meals with the whole crew and look out the window, tell stories, and that sort of thing. It's a nice day.
Question here in the front, and then we'll go to social media.
With the issue they had with the humidity or water in the spacesuit a few days ago, is that going to affect any other extra vehicular activities or repair work?
You know, that's a really good question. Right now, we've been doing some troubleshooting in the last few weeks to really zone in on exactly what part of the suit, the internal components of the suit, which part was it that failed, and then to eliminate that as a problem that could be a potential across the fleet of spacesuits. We want to make sure that it's isolated to that one suit before we sign up for other people going out the door, because that's the most important thing, is making sure that every EVA team that we send out from now on is for as a result of what we learned from these findings. So that's happening right now. I don't think that there'll be any. There's no emergent need for a spacewalk right now, and until there is, we'll make sure we'll continue the steady pace of work to find out these things, and then when the time is right and the team is happy, we'll be ready for regular routine spacewalks again. But we're not quite there yet.
Question in the front.
Hey, where were you guys a year ago on MSL's landing, and how are you celebrating today?
Gosh, we're talking about it, trying to remember where we were, and I don't remember. I remember seeing it on the news, and I remember watching, and I remember just seeing what a huge impact it was. I remember seeing a picture of Times Square where just thousands of people watching in awe. I think I might have been in Russia at the time, actually. I honestly don't remember. The past year has been such a haze of traveling back and forth for training, but I do remember, though, what an impact that it made on the entire world. And I was actually quite fascinated by that, because, and it impressed me, and I think it helped with the way social media is working these days, and just what a fantastic job that the group at JPL did with this rover, and again, just fascinated by what an impact it had over the entire world.
Okay, we'll take a question from social media.
Sure. Twitter user Micah Winston asks, what would you say is the most interesting experiment being done on the ISS right now?
It's hard to hone in on a most interesting because there's such a breadth of different topics that we're studying. Some of those that I think we find the most interest in are the ones that they're doing on the human body, and partly because we're the actual subjects for them, and so we're intimately involved in the experiments. But also in the regard that it's something that's very important. If we're going to be traveling farther away from low Earth orbit, it's obviously going to be a very long trip, and what happens to our bodies, not just how they change with the lack of gravity, but to be sure that we're going to be in shape to do work when we get wherever we're going. If we make a trip to Mars, there will be some gravity when we get there. And if we just let our bodies adapt to what a zero gravity environment is, then we will be pretty much useless when we get there, unable to stand, unable to walk, unable to our muscles will have degraded, our bones will have degraded. So I think some of the most interesting in that regard is the work that we're doing on what's happening to the human body.
Sure. We have another question here from Twitter from Chris Connors. What is your favorite task to do aboard the ISS?
Well, let's see. There's a sort of silly answer is we have when something needs to be stored up in the JLP, the Japanese logistic area, and if we're in node 1, that's about as far as you can go in a translation. So it's really fun to go flying in a controlled way, but flying around the corners to make that stowage happen. That's a sort of a silly answer to a fun thing. But on a more work-related basis, I find it rewarding to fix things. And just like in your house, things break up here or they need maintenance and attention. And it's really rewarding when the ground team puts together a procedure and we work that procedure and as a team we repair a broken pump or a broken fan or something like that. I think that's really rewarding and find that really fun.
I saw Karen post a picture of a constellation a few weeks ago, and I'm just wondering, compared to here on Earth, how do the stars and constellations compare?
All the external are off, and then all of the lights we have inside the node 3 area where our cupola is, where we look, and your eyes start to adjust. It's amazing. And I remember on my first shuttle flight when we turned off all the lights when we weren't. Without looking through the atmosphere, you don't see the same twinkle that you do of the stars. They're very solid and very, very bright. And you could also very easily pick out the Milky Way. And you start to see contrast in the dark sky. It's very beautiful.
Now that you've left Earth, how do you view it? Do you view it differently?
That's a fun thing to think about. And I like to think of myself as a little element on a mapping program, Google Earth or something, and zoom out from whatever area I'm looking at and up to the perspective that I'm looking at from the space station. And that's a fun mental exercise to do. That's just the visual aspect. But I think your question is probably deeper than that, talking about how do I personally think about the planet. And what strikes me is its beautiful simplicity, and it's our own spaceship for all of us, and that we as a whole mankind need to take care of that spaceship. And that's what being up here has really given me the perspective on the importance of taking care of our planet Earth.
I see a young blue suit astronaut in training in the audience who has a question for you too.
Why do you guys live in the International Space Station?
Why do you live in the International Space Station?
Well, one of the main things that we want to do here at the International Space Station, as you can see, we have no gravity. I'm going to lose myself. And there are a lot of things we can study without gravity. When you're on Earth, you drop something and it falls. And it affects absolutely everything when gravity pulls on it. And so what we can do here is study how liquids and various things work and what they want to do on their own without that pull of gravity. And that's very important for helping solve some of the questions that scientists have about how things work on the Earth. And it also is very important for us to answer some of the questions of how we can travel even further than the International Space Station and explore, just like it's our human nature to do.
From Twitter user Leah Crane, can you see meteors burning up in the atmosphere from space?
Actually, yes. I haven't seen one since I've been up here in the past couple months, but I do remember on my shuttle flight, perhaps it was that period of time when we were all in the flight deck looking out the windows, that we could see shooting stars below us. It was pretty neat.
Go ahead.
Hi, what are some challenges to everyday life in zero gravity environment?
Well, like Karen was just talking about gravity, the absence of it can be a challenge. It can also be very helpful when we're working. Obviously, with large mass things, it's nice not to have that gravity pull. But with smaller things, it's actually pretty inconvenient. If you're taking apart something with screws or small parts, what do you do with all those items? And we use gray tape, for instance, and stick things to that, or we'll put, if it's a larger item, we'll put it up against the inlet of a fan and it'll hold it in place. Those kind of things are everyday challenges that we face as we work up here. And then the challenges to ourselves is if we did not do any exercise, I'm sure you've heard about this, our bones would just atrophy and they would think, I don't need to work, so I can quit doing my bone thing here. And our job is to consistently work those bones so that we minimize that bone density loss when we get back to the Earth. So those are a few challenges that we have on ourselves and our daily life.
We have another question here from Twitter user Isgamore. The idea of extending ISS beyond 2020 seems to be a given. Are there any real hurdles that must be cleared besides political?
I think one of the big things is that things tend to break down after they've been used for a certain amount of time. And engineers that built and designed and built the space station tried really hard to use equipment that had long lifetime. But you think about in your own home, an air conditioning unit is only going to last for so many years before you either have to replace the entire thing or replace one of the pieces of it. And here on the space station, luckily we do have the access of various cargo vehicles that can bring up spare parts. But as the station ages, I think more and more things might start breaking, and it's hard to anticipate exactly what's going to break. Like with the spacesuit problem we had a couple weeks ago, nobody probably ever would have thought that we would have had that malfunction, but we did, and I think that's bound to happen. And so I think that will be a struggle as we continue on, but not something that's insurmountable.
Yeah, besides the fun of flying from one end of the space station to the other, given the little bit of free time that you do get, how much time do you spend just looking out the window in the cupola? And then also, could you describe the first time on station when you went in there, what that feeling was like looking out those windows?
Yeah, you hit the nail on the head. The cupola is just a magnificent place to go. And when both Karen and I were here on our shuttle flights, that cupola was not part of the space station. So for me, the first time seeing it for real with my own eyes was when I arrived here several months ago. And just like you alluded to, it's breathtaking. I mean, I remember actually the first time is when I opened the window shutters myself. So each of the windows has a shutter that you can open it with a manual turn. And as I did, I remember just looking out there and seeing the Earth out of one window, then another window, and another window, and it seemed like I was in my own real-life IMAX movie or something, 360 degrees of the Earth. And the other thing that's interesting that you don't really think about is it's on the bottom of the space station, and you go in there, and your head is directly to the Earth, so you're upside down. And it's a little disorienting at first, as if you were in an airplane and you go inverted and you're flying over an area that you're familiar with, like your hometown or something. You look left and you look right, and you have to reorient your brain. And that took me some time getting used to, okay, left means right, right means left, and that sort of thing. So it's just a really, really neat place to go. And I think the first part of your question is how much time do we spend there? Well, as much time as we can. After our evening DPC, Daily Planning Conference, we'll have dinner, and then usually people trickle up to the cupola to take pictures and see where we are on the planet and just look before going to bed.
Twitter user Chief RA asks, do you feel ready to go to Mars if you could leave right now?
That's an interesting question to try to answer. I think, I could look at it personally, me ready or us ready. Again, we could go back looking at us and whether people are ready to go in general. The problems, like I just talked about, fixing things. We have to remember that when we start a trip to Mars, we're not going to have those cargo vehicles to come and resupply us. We're not going to have the cargo vehicles to send up at the last moment a spare part that we didn't realize we were going to need. And so, the work we're doing here on the space station, just running the space station on a day-to-day basis, I think is a good test bed for what we're going to need to go to Mars. But I think there's still some work to be done. I am confident we'll get there, but I think there's just a lot of things to think about, knowing that it's a trip that can't be resupplied, can't be, once you're going. And, I think we'll get there eventually, but I think right now there's still a lot of work to do.
Okay, one more question from the audience.
Banking off of the cupola, we know that Luca seems to have an affinity of imaging Italy. Since we know that Chris is tweetless, what are your favorite spots of Earth to take photos of?
Well, thank you for giving me opportunity to answer this question with more than 140 characters. My favorite place to look is, I've said this a couple times and I really mean it. It's where the oceans meet river areas, the river deltas and things. You just get really, really interesting and neat patterns in the ocean and where the brown river meets the blues of the ocean, and you can see the tidal patterns and things like this. I just find that really, really cool. So that's the area that I like to look around, and usually there's a lot of cities obviously around the oceans as well. So at night, it's an easier place to find major cities, and you can kind of direct your vision. Okay, that's Washington, D.C., New York, there's Boston, kind of a thing, and as you go up the coastline. So I have an affinity for the coastline. Maybe it's my Navy background, I don't know.
Karen, Chris, I know we lose you in just a couple of minutes, so to close us out as our final speaker for the day to say a few words to you, it's NASA Administrator Charlie Bolden. Charlie.
Hi, Karen and Chris. I know you all have to get back to work, but let me thank you very much for sharing your time with us today. It's fascinating watching you, and I listened to the questions thinking of how I might have answered them, and I realized how old I am and how long it's been since I was where you are. But I want to thank you for everything. I want to thank you for just the tremendous job of outreach that you have been doing throughout your time there. And congratulations. We're celebrating a great anniversary here today, anniversary of Curiosity's landing. And I know where I was because I was sweating beads at JPL. So thanks to you all again. Have a great day.
Thank you, sir. It was an honor to be with you today. Thank you very much.
Congratulations to the entire Mars Curiosity team.
Thanks so much. And let me, again, welcome all of you here today and actually to thank you for coming out and helping us celebrate the 1-year anniversary of Curiosity's landing on Mars. As I just mentioned to Chris and Karen, I was privileged to be in the control center at JPL, and we were literally sweating beads and biting our fingernails, as some of you may remember from wherever you looked. I think it's incredibly fitting that we ended today's formal presentations with a conversation with our astronauts on board the International Space Station, because station is our toehold on the universe. It is, in fact, our waypoint to Mars, and it is, in fact, probably the last outpost of humanity before we find ourselves permanently on Mars one of these days. You've heard a lot about the amazing launch, the 7 minutes of terror, the entry and landing on Mars, and almost daily breakthrough discoveries that Curiosity continues to make over these past 12 months. We've talked about other robotic missions to the Red Planet that NASA's now planning, and I just want to spend a few moments talking about why Mars is the linchpin of NASA's planetary exploration strategy, and how Curiosity and other robotic missions are setting the stage for the main event, a human mission to Mars in the 2030s. First of all, why Mars? Hopefully everybody in this room has an answer to that. Or some of you may be sitting here and you came out because you don't know, and you're skeptical, and you say, I think it's stupid. Why do we want to do that? It costs much, it's dangerous, it takes a lot of time, so why Mars? First, let me say that Mars is the most Earth-like of any of the planets in our solar system, and so it's why we choose to explore it. If life exists beyond Earth, and I am one who believes that it may, very well, Mars for me is the most likely place that life will be found. What we can learn from Mars about our own Earth, and what we can learn about Mars from further studies, will improve our understanding of planetary and biological processes that affect the Earth and our life here, from the core of our Earth to the top of our atmosphere. Our conversation with astronauts today reminds us that ISS is our springboard to NASA's next big leap in exploration. Our activities and experiences on the ISS are significantly contributing to sending humans to Mars. In fact, when we sit around in quiet meetings, if there are any such thing here at NASA headquarters, but when we sit around in our meetings, our safety guys always remind us as we deliberate on what next. They ask us over and over, are we serious about going to Mars? We say, yep. They say, okay, is what we're about to do going to contribute to going to Mars? We say, yep. They said, all right, we're okay with it, because we shouldn't be putting people at risk if we're not really trying to go there. Because we're hanging it out every once in a while, and we're doing some pretty risky stuff, and we're going to do things that are even more risky than anything you've ever seen NASA attempt before in the coming years. So, we need to make sure that everything we do is significantly contributing to sending humans to Mars. NASA and our international partners are confronting challenges on a daily basis that are critical to sending humans to Mars. This includes life support systems and the challenges in maintaining them. You heard Chris and Karen in their conversation. What did Karen say? Who would have ever thought we'd have had a water leak, the magnitude that we had on the EMU, on the spacesuit, until it actually happened? If that had been on the way to Mars, there's no getting a replacement unit from the ground. There's no getting any tools from the ground the way that we're doing to help us troubleshoot the EMU right now. So we've got to make sure that the systems are solid when we send a crew on the way to Mars. There are things about the human body in the microgravity environment that we still don't understand, and so human health and performance becomes most important to us. And Chris alluded to it again. We have to remember, when we go to Mars, it is not like going to the International Space Station. When we go to station, we go prepared to live 6 months in a microgravity environment. When we go to Mars, we're going to have to prepare to live 8 months in a microgravity environment, only to transfer to a gravity environment where we're going to be for at least a year and maybe even more time. The body has not done that before, where it goes microgravity to a gravity environment for a temporary stay, back into microgravity, and then back to Earth. So challenges abound. We're using ISS as a test bed for technologies and systems, and you heard some of the presenters this morning talk about those technologies and systems that are under development for Mars exploration with humans. As you've heard, our goals include both new path-breaking robotic missions to Mars and a groundbreaking asteroid mission on the way to our ultimate goal of humans on Mars. So the wheels of Curiosity are literally blazing the trail for human footprints on Mars. Our success in landing a heavier payload on Mars with increased precision brings us closer to developing capabilities necessary for human missions to Mars. Measurements taken by MSL as it delivered the Curiosity rover to Mars last year have provided NASA the information to help design systems to protect human explorers from radiation exposure in future deep space missions. And, as you have also heard, our recently announced mission to identify, capture, redirect, and sample an asteroid would mark an unprecedented technological achievement to help reach the President's goal of sending humans to Mars in the 2030s. It's important to remember that the U.S., through NASA, was the first and still the only nation to land humans on the moon in 1969. And after that, we're determined that America leads the way to first footprints on Mars. We know we could not do the amazing things we do without the support of the President, the Congress, and most importantly, you, the American people. So, as we wish Curiosity a happy first birthday, we offer you our thanks. With your continued interest and support, I have no doubt that America will remain the world's leading spacefaring nation as we move towards sending humans farther into space than we've ever gone before, including an asteroid in Mars. Once only dreams, these goals are now within our grasp. And we hope you're as excited as we are about accepting this challenge. Thank you again for coming today. And I think there's a little time for a few questions if you have them. You won't let me get away
Questions here for the administrator? Charlie, let me start off. There's one thing I like to remind people. We didn't get to tell a lot of the Orion SLS story because we were focused on overcoming some of the challenges and ways we're doing that. Can you say just a couple of words about some of the hardware we're building, the new rocket and spacecraft
sure
that will help
can.
enable this path to Mars?
I think somebody's talked already, or at least hopefully someone's talked today a little bit about our commercial ventures. We already have 2 commercial providers that are taking cargo, or at least 2 that will be taking cargo. SpaceX has had 2 successful launches with their Dragon module taking cargo to station, and Antares will be launching the Cygnus module for orbital sciences hopefully next month. So that'll give us a second American company taking cargo. Then we have Boeing, SpaceX, and Sierra Nevada that are vying for the opportunity to begin to take our astronauts from Earth to the International Space Station and other low Earth orbit destinations. What that's allowed us to do is to get out of the low Earth orbit business, to get out of the access to space business, and really focus on putting together the systems that will allow us to take humans, take our astronauts to asteroids and onto Mars and perhaps even other places. And those 2 vehicles that we have chosen are called the SLS right now, lacking a name, and everybody's pressing me to get a name, but I like SLS, the Space Launch System, or Heavy Lift Launch Vehicle, and Orion, the crew module. Its formal name is Multi-Purpose Crew Vehicle. They are well on their way to being developed. We just finished what we call a preliminary design review, which was a very critical milestone for SLS up at the Marshall Space Flight Center just last month. We'll have a similar milestone come for Orion this fall, and that'll tell us that we're on a steady path to having both of these vehicles ready to fly. Orion, the crew vehicle, in a shell of a form, will fly its first time the fall of next year, fall of 2014. We'll launch it on a Delta IV rocket from Cape Canaveral, Florida, and send it into an orbit that will get it high enough and fast enough such that when it comes back to re-enter Earth's atmosphere, it's going at about the speeds that we would fly for a mission back from the moon or from Mars. So we want to demonstrate that it can withstand the pressures and temperatures of re-entry at those speeds. SLS is scheduled for its first flight in 2017 We'll put it together again with an uncrewed Orion module, and that'll be the first time that you actually see us launch and fly them as an integrated system. And that's leading us to a hopefully 2020 mission of SLS on Orion with a crewed vehicle this time. And if all goes well, and the asteroid initiative that I think we may have talked to you a little bit about earlier today, if all that works out and we have an asteroid that's in place in orbit around the moon, then that mission may actually be one of the first times that humans have an opportunity to encounter an asteroid. But that's sort of a SLS and Orion in a nutshell.
Perfect. We have a question here in the middle.
Yeah.
Other than budget, what are the biggest political hurdles that the organization faces, and how can we all help?
You know, I can't tell you to go talk to your congressman, but talk to your congressmen and senators. Yeah, the political hurdle right now is the same thing that all of you face as American citizens. You want things done. And we need for all of us, both the administration and the Congress, to begin to come together and focus on the future, focus on what it is that made America great and will keep us great. At the pace we're going right now, you know, we stand in jeopardy of not being the great nation that we always have been and that all of us expect to be. So I'm certain that the political powers here in town will come together over time. You can already hear conversation and inklings that people are starting to realize that, you know, there are important things to be done. But doing things like deep space exploration require willpower more than much other things. We went to the moon because of President John F. Kennedy, who did not live to see it, but who had a vision that humans should someday, and he was very specific, before the end of that decade, before the end of the 60s, we should go to the moon with men then and bring them safely back to Earth. And this president has told us, and he wants it to be in his lifetime, but he knows it won't be in his presidency because it's the 2030s. And so he wants us to send humans to Mars and bring them safely back home. And I think we can do that. But it's going to take combined willpower on the part of both the administration, the Congress, well, all three, the administration, the Congress, and the public, not the American public, but the world public. This is not going to be a U.S. venture. We'll lead it, but we can't do it without the assistance of other nations.
Charlie, I know you have administrator things to do, so we'll let you go run back to running NASA.
Thank you all very much, and thanks so much for coming out today.
Thanks so much, Charlie. All right, so that's going to conclude today's event. As I said at the outset, it's a very special day in recent NASA history, this first anniversary of Curiosity's landing on Mars. For all the things we talked about, for more Curiosity science, for the follow-on missions like MAVEN that are coming, for new NASA technologies and development, to keep up with the International Space Station crew, please visit nasa.gov for that and more. You can find all the ways to connect with us and engage with us on social media still, and continue this conversation at nasa.gov/connect. Of course, you can find us at Mars and at NASA and at Mars Curiosity on Twitter. And the hashtag we'll be using is 1 year on Mars to continue the conversation about this special event. So that's going to do it from NASA headquarters. I'm Trent Parado. Thank you for joining us.